Imagine you've trained a giant language model on half the internet, and then someone says, "That copyrighted book in your training data. You have to forget it." Not hide it, actually forget it. The obvious fix, retrain from scratch without the book, costs a fortune. This paper from Microsoft asks, can we make a model selectively forget, surgically, in about an hour? Here's the core tension. These models are trained on massive internet corpora that often contain copyrighted content, private data, or toxic text. Once it's baked in, there's no obvious delete button. Fine-tuning is great at adding knowledge, but nobody knew how to reliably remove it. And retraining a model from zero is absurdly expensive. And the result is striking. The original Llama 2.7b model from Meta took over 184,000 GPU hours to train. This technique erases its knowledge of the entire Harry Potter series in about 1 GPU hour of fine-tuning, while its scores on standard benchmarks like Winogrand and Hellaswag stay almost untouched. Look at what that does in practice, straight from the paper. Same prompts, 2 models. On the left, the original model knows everything. Harry's best friends are Ron and Hermione. He studies at Hogwarts. On the right, after unlearning, the same prompts produce something plausible but generic. Harry Potter becomes a British actor. His best friends become a talking cat and a dragon. The knowledge is genuinely gone. Let's define the goal precisely. The model was trained on a dataset X. We pick a subset Y, the unlearned target here, the Harry Potter books. We want to mimic the effect of having retrained on everything except Y, but without the cost. So what's the obvious first attempt? The naive idea is gradient ascent. Whenever the model correctly predicts the next word in the book, punish it, flip the loss. But this fails badly. Consider Harry Potter went up to him and said, "Hello, my name is." If the next word is Harry, negating the loss doesn't teach it to forget the books. It teaches it to forget the meaning of the phrase "my name is." You damage general language, not specific knowledge. There's a second, subtler failure. Take Harry Potter's 2 best friends are. The model gives nearly all its probability to Ron or Hermione. Suppress Ron, and it just shifts to Hermione. Suppress that, and it finds another book term. You're playing whack-a-mole. What the model really needs is a plausible non-magical answer to put there instead. That reframes the entire problem into one clean question. For every single token in the book, we need to answer, what would a model that had never read Harry Potter have predicted here? The authors call this the generic prediction. If we can generate those, we can fine-tune the model to produce them, and the magic quietly drains away. They build 2 methods to find it. The first method is a clever trick called reinforcement bootstrapping. We can't easily untrain on the books, but the opposite is trivial: train harder on them. So they fine-tune the model further on Harry Potter to create a reinforced model, one that's even more obsessed with the series than the original. Here's the insight. Compare the 2 models' logits, their raw token scores. Tokens whose scores shot up after extra Harry Potter training are clearly the book-specific ones, like Ron or Hogwarts. Tokens whose scores didn't move are the generic, language-level ones. So the direction of change points straight at the knowledge we want to remove. They turn this into a formula. Generic logits equal the baseline logits, minus a coefficient alpha times the reinforced minus baseline difference, passed through a ReLU. In plain terms, take the model's normal predictions, then push down exactly the tokens that got more Harry Potter-ish under reinforcement. The ReLU means we only subtract where knowledge increased, never add it back. But this alone isn't enough. If the model is primed with a strong cue, say the name Harry on the scar, the book completion already sits near 100% probability, and extra reinforcement barely nudges it. The signal vanishes. So for the strongest, most idiosyncratic cues, they need a second, sharper tool. The second method is the real heart of the technique, anchored terms. The key reframing is subtle but powerful. The goal isn't to forget the word Harry. It's to forget the link between the entity Harry Potter and the entity magic. Break the associations, not the vocabulary. To do this, they use GPT-4 for entity extraction. They feed it passages and ask it to list every idiosyncratic term, names, places, spells, and pair each with a generic substitute. Hogwarts becomes Mystic Academy. Quidditch becomes Skyball. Ron becomes Tom. They built a dictionary of about 1,500 of these anchored generic mappings. Now the clever part. Take a block of the book and swap the anchor terms for their generic versions. Then run this translated text through the original model and record its next token predictions. Crucially, you then map those predictions back onto the original, untranslated text. So the model learns, even when primed with real Harry Potter context, predict the generic continuation. Think about why this is so elegant. Generic text no longer triggers the magical associations, so the model gives an ordinary, sensible continuation. By teaching the model to produce that ordinary continuation when it sees the real, untouched Harry Potter context, you sever the association at its source, while keeping the sentence perfectly fluent. There's one nasty edge case. Take Harry went up and said, "Hi, my name is Harry." Naively swapping would train the model on, "My name is John," an inconsistency that confuses it. So they add fixes. An anchor that already appeared in a block isn't swapped again, and they suppress the logits of translations that already appeared. Consistency preserved. Now combine everything. For each block, they get the reinforced predictions and the anchored generic predictions, merge them with that ReLU formula, and pick the top token as the final generic label. Then they simply fine-tune the original model. Original text as input, generic labels as targets. Around 150 gradient steps is enough. The intuition in one line. Every time the original text would have primed the model toward a Harry Potter token, the fine-tuning gently steers it toward a generic one instead. Repeat across the whole book, and the model is systematically pushed off its magical attractors and onto ordinary ones. How do you even measure forgetting? On two axes. First, preservation. Does it still ace general benchmarks? Second, eradication. A battery of black box tests, 300 curated prompts plus token probability checks, all trying to coax out any lingering Harry Potter knowledge. They even open-sourced the model so the community could attack it. The numbers are convincing. Their familiarity score, how much Harry Potter knowledge leaks out, starts at 0.29 for the original model and collapses towards 0 within about 100 fine-tuning steps. Meanwhile, the benchmark scores stay essentially flat. The knowledge drains away, the general intelligence stays put. An ablation confirms you need both ingredients. Reinforcement alone barely dents familiarity. It fails on basic prompts like Harry Potter's best friends are. Anchoring alone works better but hurts general benchmarks when pushed to the same forgetting level. Only the combination achieves deep forgetting while keeping the model sharp. The authors are refreshingly honest about limits. A few leaks survive. Ask for fictional schools and Hogwarts may slip out, though only at Wikipedia depth, not book detail. The method leans on Harry Potter's dense, idiosyncratic vocabulary and on GPT-4's prior knowledge. For nonfiction or textbooks, which encode abstract ideas instead of unique names, it's much harder. Still, this was the first effective unlearning technique for generative language models, and it reframed an impossible-sounding problem into a tractable one. Beyond copyright, it points toward models you can edit after training, to strip private data, remove toxic content, or align with new rules, without burning a fortune retraining from scratch. So here's the one-line takeaway. You can't easily untrain a model, but you can teach it the boring answer. Find what a Potter-free model would have said, using a reinforced model and a dictionary of anchored terms, then fine-tune toward those generic predictions. In one GPU hour, the magic is gone. Thanks for watching.